My name is Alice Cocoros. I am a physicist at APL. That means I do a really wide range of things. My background is in particle physics. This is what I got my PhD in. But at this point now, a lot of the work I do involves systems engineering for instrument-related things on various missions. So I work on the Dragonfly mission, and I've been working on a concept study called Interstellar Probe. And then I also do some work serving on a consortium that's trying to help NASA figure out how we can establish a presence on the moon. So the Dragonfly mission is super exciting. It is NASA's latest New Frontiers mission that's been selected. And so our goal is to send a nuclear-powered octocopter, which is a helicopter with 8 rotors, to the surface of Titan, which is one of Saturn's moons. And what's really interesting about Titan is that it is one of the ocean worlds of our solar system. And what's also really interesting about it is it has a really thick atmosphere and pretty low gravity, which actually makes it pretty easy to fly on Titan. So I've heard a number of the people involved in the mission say that if you strapped wings to yourself and flapped on the surface of Titan, even you could fly. So that makes it a really unique mission in terms of the excitingness of being able to go to an ocean world and look at prebiotic chemistry that might give us some insight into how life forms and what may or may not be on Titan. But we also have this really unique way of being able to navigate and cover a decent amount of the surface of Titan because of the environment. So my role on Dragonfly is that I'm part of the mobility subsystem. And so the mobility subsystem is in charge of navigation on Titan. So there's no GPS, obviously. We only have GPS here on Earth. So you have to find some way to know where you are and know where you're going so that you can reach all the science goals you want to reach in terms of seeing all the different sites you want to see, but also not get lost and keep the rotorcraft safe. So specifically on the mobility subsystem, I'm part of the LiDAR team. So the LiDAR is doing hazard avoidance, which means we shine lasers down on the surface and those lasers reflect back up, and we're able to look at images, and using algorithms, we process all of that data to analyze whether the terrain underneath us is safe for landing, which means that it's not too slopey and it doesn't have too many rocks around, or whether it's not safe and we need to keep moving and find a safer landing site. One of the big challenges is that all of this has to happen autonomously, because the light time in terms of communication from Earth to Titan is pretty long. The whole system has to be able to navigate the surface of Titan without a human in the loop. Machine learning is a really useful tool when you have big data sets and something you want to pick out from that data set that might not necessarily be obvious by other methods. So along with a couple colleagues, I did kind of proof of principle concept to look at whether we could take high contrast images in the infrared of exoplanets, which were taken with the Gemini Planet Imager, which is on the Gemini South Telescope in Chile, and whether we would be able to train a neural network on those to be able to detect exoplanets from that, because they found a lot less exoplanets than they had expected. And because in the future, we're going to need more robust algorithms than the current baseline algorithms to be able to detect Earth-like planets, which are much, much fainter than the current planets we can image, which are what are called hot Jupiters, which means they're really big and really hot. So they're really bright. They're kind of like the low-hanging fruit, which is a strong statement because it's really hard to image, like directly image exoplanets in the first place. But with bigger telescopes, we expect that we would be able to image those Earth-like planets around sun-like stars, but we would need some improvements in algorithms and not just the instrumentation to be able to do that. So I had a lot of different interests growing up. I think when I was in elementary school, I wanted to be a vet. Throughout middle school and probably like the first half of high school, I wanted to be an actress. And then I'm specifically a Broadway actress. So I was really into not only acting, but also singing and dancing. Um, in college, I kind of refocused that performing arts into piano and was debating between becoming a physicist. So I did go to college for physics, but I also went to college for music and was kind of trying to debate which one I wanted to do. And so my junior year of college, I spent like the first semester, I spent my fall semester focused on music and, did a concert on my own and kind of really honed in on that. And then I spent the second semester at CERN, which is the Center for Nuclear Research in Switzerland that houses the Large Hadron Collider, which is the big giant particle collider, which found the Higgs boson back in 2012, which happened to coincide with when I was there. So that was really exciting. And as much as I love piano, I just really kind of fell in love with particle physics. And it was so exciting to be there when it hadn't quite gone public to the world, but we were really pretty sure as a collaboration. So at that time, I was part of the ATLAS collaboration, which is one of the 4 major detectors on the Large Hadron Collider, one of the 2 major ones that does general particle physics rather than focused on like specific topics. And then they were one of the 2 that, would go on to announce that we had in fact found the Higgs boson. For those who don't know, particles kind of talk to each other and that's how they interact, so to speak. And particles that quote unquote talk to the Higgs boson are massive, such as an electron, but particles that don't, such as a photon, are massless. So that's kind of the function of the Higgs boson and explains a lot about the standard model of particle physics, which is basically everything we know about interactions at that quantum level, with still a lot of gaps and questions to be learned. So I fell in love with particle physics at that point and knew I wanted to get my PhD in that. So I came back and I ended up going to Johns Hopkins for my PhD and had a really great experience and did consider moving on in that field. But I ended up deciding that academia wasn't quite the right fit for me. It would have required too many moves to different places and too long to achieve like full tenure as a professor. You're just like, 35 or 40 or something by the time you achieve tenure. And it just felt a little bit longer than I wanted to wait to have like a stable and set job. So I had gotten my bachelor's in astrophysics actually originally. So I kind of went back into space and decided that APL would be a really good place for me to use all my skills, which range from being able to perform fundamental research to data analysis, a lot of different things that I had learned over the course of my bachelor's and PhD towards space missions, which I found very exciting as well. So I do miss particle physics every once in a while, but I'm really happy with the career decision I've made. My favorite class that I took, if I have to pick one, would be general relativity. So I went to a liberal arts college called Williams College, which has a close tie to Oxford, which has a methodology of some of their courses where 2 people take a course with 1 professor, and that's it. That's the course. And you do it in such a manner that the professor kind of teaches a lecture and then you like go off and do a bunch of work and then you come back and he teaches another lecture, and it's a much more interactive style of teaching. So my best friend and I, we took this course together with a visiting professor who's from Poland, who we absolutely adored, Professor Demianski. He was wonderful. It was surprising to come to APL and suddenly not be defined by the precise research that I had previously done. They really kind of like opened the table for me and said like, what do you want to work on? What interests you? And kind of let me learn new things as I went along on the job. And that was a different experience for me from traditional academia, where you really have to pay your dues in a very precise way to advance your career. They look really different depending on what's going on at the moment. So I'd say some days look like a lot of Zoom meetings and a lot of PowerPoints, writing papers, or, writing up requirement documents, or just a lot of that type of work. Some days might look like field testing. In March, we took a developmental model of a LiDAR to a test facility in Colorado. And so that looked like, running the LiDAR through a bunch of different tests and looking at the data and making sure it worked all right. So it can look like that sometimes. And sometimes it looks like, really hunkering down and doing the technical work that needs to be done, which for me is occasionally in the lab with hardware, but for the most part, usually analysis based on the computer. I have a good one. That's been my goal from day one. And actually a big reason I left academia was the chronic bad work-life balance that a lot of assistant professors have, because they have to, because they're in this what's called publish or perish regime, where they really have to get out a certain number of papers to guarantee themselves tenure. And there's really no limit to the work week. You rarely work over 40 hours, but I fill those 40 hours very well with a lot of work. I'm a mom to an 11-month-old, and I've felt, through that process of becoming a mom and learning to balance having an infant during a pandemic while working from home. I really like working for a place that values me as a human and not just a physicist. For a job like mine, I think, general knowledge of science of whatever you're doing, which, really might range depending on the mission, is important. I think capability with software. I never took a formal computer science class, but I've been coding since undergrad. So I've been coding for probably about 10 years now. I think and at this point, I think I was really on the cusp of that being less important. And nowadays it's extremely important. I don't think people even graduate high school without starting to code who are interested in STEM. So I think that's pretty critical. I think being able to communicate your research, being able to effectively write papers or, give a PowerPoint presentation at an audience appropriate level is critical, because if you can't disseminate what you're working on appropriately, then it won't go as far. Soft skills, I think listening is really important. So not only do I serve as a technical lead on a number of programs at APL, but I'm also a line manager. So I'm the section supervisor for the advanced algorithm section in our science and space instrumentation branch. So I manage a small group of staff and make sure that their careers are progressing the way they want them to, and kind of help them out with any challenges they might come across. And listening is probably one of the most important things I could do as a manager. I would tell a high school student who's headed into undergrad not to get discouraged by the first year or two, because those introductory courses can be really brutal, especially depending. So I grew up in rural Nevada, so I was not prepared well for going to a school where a lot of my fellow students, had had a prep school education for high school. So we had vastly different experiences. And I really had a tough time those first years kind of playing catch up. And, plenty of other people had a hard time for different reasons. Physics is hard, astrophysics is hard. But it gets easier with time as you kind of learn how to problem solve in that way. So I definitely tell people that if they're really interested in it, but they're not sure they're good at it, to just stick it through and kind of give it a few years before they give up on it. And then I would tell an undergrad who's interested in graduate school to first think very carefully about whether they really want to go to graduate school, because it's a pretty challenging thing to undertake. And if you don't really, really want it, you might end up miserable. But if it's what they really, really want, then I would definitely encourage it. I'm so glad I got my PhD, and I really enjoyed that experience of focusing in on research. And I was blessed to have a really great graduate school advisor. So I'd also advise to choose your graduate school advisor carefully.